fill in my All right, hello everybody. I hope everyone is doing well. I just realized I didn't have my drawing program open. Let me just open that. Might learn spell. T. Just opening up what we need to. So we have looked at conditional probability a little bit. I don't think I actually opened it. It's not starting. Oh no, there it is. Never mind. We looked at conditional probability a little bit, but I think it should be obvious to everyone that we need to have a continuing discussion before it really feels better. Let me start by just sort of mapping out, and I literally thought about this like a minute ago. It might be useful to sort of map out where we're at when we approach a question involving probabilities. What decisions do I make, regardless of the specific question? Recognizing it as a probability question is not going to be too hard. It'll be long and wordy and have different events and probabilities. You'll notice it when you start looking at the problems. So let's say here, this is my thought process, and it's not uh, set in stone. Feel free to adapt it. I'm making this up right now, just thinking about what could be an efficient way to get through this. So, the first thing I have to do is identify what the properties or events. I don't have to think about it in terms of sets necessarily. I just want to think about it as like I'm selecting people, and those people have certain properties, male, female. Those stand opposite to each other in my visualization of what could happen in province, out of province, and things like that. In this question, what are the things that they're talking about? Okay, for future reference, just as a side note, anyone who doesn't have their mic muted and I can hear is not using push to talk, I'm muting because it annoys people to have background noise from someone else, right? Okay, anyway. So I have to just identify. I don't need to understand the question perfectly, but just what are the things that they're talking about? Am I selecting people? Am I rolling dice? Am I drawing objects from a bag? Whatever, right? And what properties could those things have? And then decide on whether you want to use a table or a tree diagram. Usually, whatever I decide to make, usually it'll be a tree diagram because I can't effectively, in my opinion, use a table for every kind of question, but I can effectively use a tree diagram for every kind of question. So this is going to be my preferred option. But if they give me straight up numbers, like our very first example, a table can be sufficient in simple cases. More complicated cases, tree diagram would be preferred, and it covers whatever the table can do anyway. So unless the question specifically says make a table, you can choose whatever you want. So once I have, let's go with the tree diagram specifically. Then I want to fill in the events in terms of how it can split. What is the first split here? And then do I have further splits in what defines an outcome? An outcome can have multiple properties. So my tree is sort of conceptually creating all the properties an outcome could have. Maybe a male-female split, and then in addition to that, afterwards I need to decide on an improvs outprovence property, and only then start to finish have I created an outcome, have I finished the experiment of selecting a person in this way. So I want to map things out, and then I want to, assuming you're doing a tree, which is most often going to be unless they force me to make a table, and then it's much simpler, so I'll skip that. Fill in the events, fill in the probabilities, probs on the branches. And we talked about yesterday how some of these are straightforward conventional probabilities. Some of them deeper into the tree will be conditional probabilities. Given I've taken this step, what is the probability of the next thing happening? So of course the tree has to be set up in a way that I can fill in all the numbers on the branches, all the properties. And they have to, in the question, mainly give me that information. And that might guide me to how to set up the tree. Once I have that, we're going to the actual questions. Go to the actual questions, where they're going to ask me, what is the probability of this happening? What is the probability of this and this, and so on. And there I have to decide, well, given a probability, go to the questions where it's asking a probability. First issue is the probability that they're asking already on the tree, already on my tree? If it is, then I'm done. I simply, because I've made my tree and that serves as my work shown, I just write down the answer from the tree and I'm done. So that's the best case scenario. That the probability they're asking, I've already done the work by setting up the tree and my work is done. Next up, if the answer is no, let's say if not. So here, if yes, it's like a flowchart, right? Without the fancy arrows and stuff. If yes, then we're done. We write down the answer, we move on with our lives. If not, let's say no rather. No is your answer. Then I have to do some work. If no, I have two choices. Is it I'll say conventional probability that they want, or is it a conditional probability that they want? And for it to be a conditional probability, there has to be some keyword, like given some information, what is the probability of something else? Or if it is known that blah, 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 what is the probability of something? Usually one of those two, but words that make it clear some extra information is provided and known, with that information known, what are some probabilities? Okay. So if it's a conventional probability, I simply identify the paths that will give me, from start to finish, that will satisfy that requirement that the probability wants. Is it the top path? Is it just the second path? Is it a couple of paths that I then add together? And we've figured out for a single path, we multiply along the path, and then we add up separate paths. If it's a conditional probability, we've already identified it's not a conditional probability on the tree, then I have to use the formula and let's say take care of the two, sorry, of the two conventional probabilities that come out of it. And here I mean like probability of E given F is the probability of the intersection divided by the probability of the given event. So then I'm rewriting my conditional probability to two conventional probabilities that I can go back and identify the paths for each one separately. Okay. So hopefully this gives you some outline for how to approach this. Still doesn't make it super easy. There's a lot of words and a lot of things to uh, interpret, but that comes with more experience. Let's open the book, and of course, I haven't done that either.
Do you have to represent the set? You know how we said let E
Uh,
represent.
yes and no. Do it if it helps you,
Okay.
but if you want to do everything in words, uh, just use an intersection so I can see that you understand the formula. Use this line for the conditional probability, but if instead of letters or names for your sets, you want to write little words there, that's okay. Many
Okay.
many new books do it that way, so that we don't get caught up in uh, that formality that doesn't actually change our understanding or improve our understanding. So I'd say that's fine as long as it's clear that you your description then has to be clear enough. So if you're not sure, maybe try that on the problems when we eventually get there. And I can check, is it clear enough? If you're not sure, it's hard to be objective. Answer is clear or not, right? So if you, I'm happy to check it if you want a way to a test. So let's look at 6.2, where we'll now keep this outline in mind for how to approach this. Now this one's nice and sectioned, clear questions because it's the first one, really. An urn contains two red and three blue balls. Let me check, you can see it, yeah. And you make two selections of one ball after another. So you select a ball and then you select another ball. Represent the different outcomes of the experiment with a tree diagram. Very often they will separate the parts to make it easier to grade. And by they, I mean me. So that in case you make a mistake, it's sort of sectioned and I can find how severe that mistake is. Because once we set up the tree diagram, we're going to just use the tree diagram. And any mistake I make in my tree diagram, if I work with that mistake, because I won't know it's a mistake, then I'm just going to keep going. Now, for simplicity, and habit really, I do like to make names for my events, but again, if you can be clear with just a few little words, that's okay too. I'm going to say let R1, because there's a first and a second selection, I need to put a number on which one's first, which one's second. Let R1 represent the event of choosing red first. And I don't need a new name for selecting a blue ball first because it'll just be the complement of this event, though you're welcome to do it uh, as a separate event, but they're complements of each other anyway. I just feel like focusing on red. It's just a choice. There are different ways to go about this. R2 is going to represent for me the event of choosing blue, not blue. I just said I don't need it. Red second. This is not the only way to do it. You might focus on blue. You might make all four events. I'm just giving you options. Now let's map this out. First, I'm going to be choosing either red for my first selection or not red, because I only have two options. One's the complement of the other one. Then I have a second selection following that. Split like this, which will then be either I select red second or I don't. Again, you can make it R and B, really doesn't matter. But in the interest of minimizing my sentences that I have to write, maybe this is preferred. So now, let's see here, we'll drag this back and forth a little bit. Doesn't get too annoying. I do, when they say tree diagram, I want to fill in the tree diagram probabilities completely. So I'm going to have to say here, 2 red, 3 blue in my earth. Let's just keep track of that. So let's make it like this here. 2 red, 3 blue. Okay, so I remember. So now, start to finish, my first step is making one selection. The probability of selecting a red ball is 2 out of 5. 2 will give me the desired result. There are 5 ways in general to choose a ball. Then, of course, blue will be 3 out of 5, right? So these probabilities hopefully aren't too complicated. Then, the next part of the tree is, given I've selected a red ball, now I'm putting my hand in the urn and drawing another one. I now have 1 out of 4 to be red, because 1 red is gone. And then still the 3 blue out of a total of 4. Given I've taken the bottom step by selecting a blue ball, I have 2 and 2. So it's 2 out of 4, 2 out of 4. I don't want to simplify these fractions or do anything with them. I just want to fill them in as is. Now I have my scenarios mapped out. Anything that could happen. Red, 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 blue, blue, red, blue, blue. Nothing else can happen. It's mapping, it's explaining the experiment completely. And I can now use this to answer literally any probability question about this experiment that they could possibly have. Okay, so now just a few probabilities here that they want. So now if I made a mistake, for example, I went too fast, I wasn't paying attention, or whatever it could be, you have to use the tree that you made moving forward. So if, for example, I accidentally wrote 2 out of 4 here, but I used that correctly, then you get all the following marks because you used your tree. But if I made a mistake here, and then later on I notice it and just start writing 3/4, no, those are 2 mistakes because you made a mistake in the tree and now you're using a fraction that doesn't come from your tree technically. So just be aware of that. Okay. What is the probability that you selected a red ball first? Now, because I have the events, I will write down maybe over here. Maybe we can see it all. Instead of going back and forth, let's see how much we can fill in on the same screen. Might be nice. I'm looking for the probability of red ball first. That's I called R1. It's just a convenience because I don't want to write the words and get all messed up. Trying to make it descriptive enough in the brackets. And I'm used to it this way. First thing I do, well, not first, I've gotten to the question part now. Is the probability already on the tree? Yes, it is. It's right there. There is nothing to do but copy it down. So easy. Of course, I'm always hoping for that easy case, but It's not always going to happen, right? When it does happen, I feel pretty good. And whatever probability you wrote down there, you copy that down. Whether it's right or not, you're showing that you're using the tree correctly. And the number that's there is the number you're writing down. That's a good start. Let's continue. Number three. Now, I don't remember. Maybe you can't see the book and the screen at the same time, so I'll drag it over here. Three. What is the probability that you selected a red ball first, then a blue ball? So now I ask myself, is that on the tree? No, because they're asking for multiple things, and none of those things are given. There's no keyword given, if, anything like that. Selecting a red ball first, then a blue ball. So in terms of my defined uh, events, I'm looking for red ball first and then uh, blue ball second. So that would be not red second. The complements bother you, just make a B1 and an R and a B2. It's the same. So now this isn't directly one of these numbers on the tree, but it is a conventional probability, which means all I need to do is find the path that satisfy, or the paths that satisfy this requirement, this restriction, this property. R1 and complement of R2. No other path will have both of those because the intersection asks for both, right? So it's that third path, if you will. And to find the probability of that path, I multiply along the, I hope, still pretty straightforward, but there is definitely a thought process, steps to go through to get there. And if you follow those steps and you understand the big picture of how to use this, it's not that bad, I hope. It's hard for me to be objective because I've done this so many times. I don't think about it almost, right? So used to the thought process because it's not new. But if it's new, it might take a while to get used to, sure. But once you do, it should be okay. Number four, what is the probability that you selected a red ball and a blue ball? Now here, they don't necessarily match the events I have. I specifically have red first, red second. All they ask for is a red and a blue ball. They don't care how. So this might be a good opportunity to not get caught up in defining events, because I said you don't have to. Just say a red ball and a blue. That's an E. Now I made it uglier. And they don't say which one's first and which one's second. So now I have to see, well, which paths can satisfy the restriction of selecting a red and a blue ball in any combination, in any order. Well, it could be red-blue, or it could be blue-red. Can't be red-red, can't be blue-blue. So I have two different paths that would satisfy this restriction. And I don't need to get caught up in defining new events because it's clear enough. And I'm copying the question to a large degree. So I'm going to look for path number two, I'll call it. The probability of that path, I multiply, or I find by multiplying along the path. Completely separate paths get added because there's no overlap. I can't have both of those paths happening. Which one was the other one? The third path. To get the probability of that path, I multiply along the path. And then calculating that is a formality, right? I'm skipping that. You can leave your answer like that too. If the question asks, calculate your probability, round it to two decimal places, or calculate your probability and state it as a percentage. Just be aware of those little things, how they want the answer. But I'm leaving those up to you because it's pretty straightforward. So whether you have events, whether you write little words there, as long as it's clear, it's totally fine. And the way they asked this number four, I didn't have events predefined, and I didn't need to. It's clear enough, I hope. Number 5. Given, keyword, given you selected a red ball first, what is the probability that you selected a red ball second? So now it takes a while, perhaps some experience, to recognize when it's a conditional probability and when it's not. That is definitely something that we have to be able to do, and there will be key words like given, if it is known. I can't think of anything else. More words may be describing the same concepts, but I have to know, I have to write, whether it's little words or completely symbolic, I have to write down the probability that's being asked. Given red ball first, probability that you selected a red ball second. Now remember, the probability, the event that they're looking for comes first in my probability representation. Red ball second, given red ball first. Don't swap these or it's wrong. Even though the sentence might swap them around, when I write the probability, I cannot. I have to do it in the right order. The given information is always after this line. So now I recognize, of course, it is a conditional probability. What do I do with that? It could be on the tree, or it could not, because the tree contains some conditional probabilities. Is this one on the tree? Yes, it is, because it's exactly in line with how I set it up. This guy is exactly, given this first thing happened, what is the probability that this happens? That's exactly what they're asking. I'll just clear the tree. So there is nothing to do. The work I put in on my tree was the work I need to show. I just need to recognize that it's right there. Easy peasy. No, not really. But it can be with some practice. Last one. What is the probability that you selected a blue ball second? Okay. I do have an event for that. Probability not red second, meaning blue second. Again, this probability is not directly on my tree because it's the second selection, not the first one. So it's deeper in, and these are conditional. And this is a conventional probability. When it's a conventional probability, I just find the paths that satisfy the event. This one and this one. Because I could select red first, then get what they're looking for, or blue first and then get what they're looking for. So two paths, top path, 2/5 times 3/4, plus the bottom possibility, 3/5 times 2/4, I guess. There we go. Make your own flowchart if you want. This isn't very pretty, but it gets the job done. And hopefully we get the idea now. Let us look at something quite practically relevant. I could have made it perfectly practically relevant, but I just took whatever the actually no, it is quite relevant. For a certain virus, there is a test to identify if a person has the virus, an unknown virus, nothing relevant to today's situation. The test is 98% accurate. What does that mean? It means that if someone has the virus, the test will say positive, you have it 98% of the time. It's not a perfect test. And if someone doesn't have the virus, it's going to say negative, meaning you don't have the virus, 98% of the time. So it's going to have an error in it, unfortunately. Assume further that, let's say 0.5% of the population actually has the virus. I've just made a little descriptive question here. A test question would be more precise. You're selected at random and tested. The test comes back positive. So the test says you have the virus. Should you be worried? Should you sell all your belongings and say your last goodbyes, depending on how deadly the virus is, of course? What what are the chances of you actually having it? So for this kind of question, we're regardless of the numbers changing, we have this sort of disease virus kind of question, and I'm almost always going to set it up in the following way. I'm going to say let V represent the event that I'm going to be very clear here because this is your first example, that a randomly selected person, could be you, has the virus, random from the population. And then my first split with some space here is going to be, oops, ah, a person, in fact, we don't necessarily know, but in fact, could have the virus or could not. Right? Those are the only two possibilities. You have it or you don't have it. Then I also want to know what the test says. So let T represent the event that the test, uh, let's say, returns. Whoops, lost the ability to write. Writing is important. Returns positive. Test says you has it. You has it. Wow. The test says that the person has it, but the test might not be correct. It's not a perfect test. So, regardless of if the person has the virus or not, the test could say positive or negative. If the person doesn't have the virus, it could still say positive or negative. Now, I don't want to use a P for positive because P is for probability. So T or not T, T or not T. Guys, that's how we're going to do it. And we're always going to do it this way, always. Because I don't know anything about the test until I give it a person that has the virus or not. I can't tell what the probabilities are, so it has to be this way. So they tell me 0.5% of the population actually has the virus, so that means zero point 0.5 out of 100. Here are probabilities on the tree. Probabilities are fractions between 0 and 1, even though in a descriptive setting, in a paragraph, in a question, they might use percentages. I never use percentages in a calculation. That's my rule for safety. Percentages are presentations of fractions and only presentations. So then the probability of actually not having the virus is 99.5%, so out of 100. Just change the percentage back to a fraction, right? Then they tell me test is 98% correct. So that means if I take this first step and have a person that has the virus, the test is going to say that they have it 98% of the time. And it's going to make the incorrect conclusion 2% of the time. When I present the test with a person that doesn't have the virus, it's going to correctly say negative 98% of the time, but it's going to sometimes say positive because it has an error built into it. Nothing is perfect. Now I have my tree filled out completely. And I admit that they don't answer the question, they don't ask the question perfectly because it's a discussion and I just want to get things started. A test question will be more precise. I want to know, I can ask many things, but my main question is, what is the probability that I uh, have the virus if my test comes back positive? So let's suppose I'm not necessarily randomly, I'm selected, I'm being tested. And the test says, yes, you have it. How concerned should I be? Well, my concern level will go with whatever this probability is, that given my test result is positive, what are the chances I actually have the virus? So this is the probability that's relevant to my life, for my concern. Okay? Because in this case, the virus is quite rare. Like 0.5% of all people have it. It's not super rare, but it's also not super common. And I don't know how that affects my chances with in combination with a test that has an error as well. I can't get a feel for whether I'm near death or should not change my life at all. I don't know because these things are combined in a weird way. I don't know. This is why we have a probability calculation to precisely know outside of my feeling. So I look at this as a conditional probability. It is not on the tree already. It's the other way around, right? These probabilities are conditional probabilities, but they are given virus. What does the test say? This is given the test result, do I have the virus? It's different. So what do I do then? It's my most difficult situation. I rewrite the conditional probability to two conventional probabilities. I'll do it below here. It's always the probability of the intersection divided by the probability of the given event. Always. Now I treat them separately. I just have two conventional probabilities and I'm back to my flowchart over here. Identify the paths and add them up if there are multiple paths. In the top case, I only have the top path. That'll give me a V and a T, only the top path. So the probability of that path I get by multiplying along the path. And it's done. Bottom one, however, I can get with the top path or with this third path because it only requires T. So there are two ways to get a positive result. It could be a correct positive result, or it could be what we call a false positive, where the person is actually not sick at all, yet the test says positive due to its error. So I have the top path, which has probability first branch times second branch, plus another way of getting it, first branch in that path times second branch in that path. Now in this case, I want to have a number. I want to know what are my chances that I uh, have the virus. So let's calculate this. And if you have a calculator in front of you, let's do it together. It might be a little quiet as I type because I can't hold down my push to talk button always and type at the same time. Discord gets angry. All right, so let's do it. So I'll do it exactly as it is there, even though I have a common denominator of 100 times 100 everywhere. Confuse everyone or anyone. So first bracket here is 0.5 divided by 100 times 98 divided by 100, and then divided by the whole denominator that I'll put in a bracket. I'm pretending you're doing this with me. 0.5 divided by 100 times 98 divided by 100 plus 99.5 divided by 100 times 2 divided by. It says, I did that without looking, so hopefully it's right. 0.1976 will round, meaning 19.76%. That is not what my intuition says. My intuition says if a test result comes back positive, I am screwed. I should be really concerned. Even though there's less than a 20% chance you have the virus, because it's quite rare. And in combination with the test procedures error, it's hard for me to feel. I just feel like, oh, the test says I'm sick. Oh no. Yeah, it's unlikely you're actually sick. I mean, 20% is nothing to be concerned. It's nothing to just dismiss immediately, but it's also not like you're gonna die tomorrow, right? There's still a lot, a high chance that you might be totally fine. So what happens in practice? What happens in practice is you cannot make any significant decision based on a single test because the probability of actually being sick, even if your test says you are, is quite low. So what happens? They make another test, a follow-up test. So this will be test one. And I invite you to do the same thing. I'll state the probability in a second. So they make another test, regardless of what the first test says. Test again. That test is going to come out positive or not. Test again, test again, test again. And then you want to know, well, given I have a positive test and then another positive test, what are the chances that I actually have the virus? Then you see, well, if I get two positive tests, then this probability of actually having the virus just jumps up. Then it's much, much more likely. So then this obviously is not on the tree. So here I would still have 98 and 100 and 2 over 100, right? Similar test error. So here I would have the probability of the intersection of everything divided by the probability of the given event. Same thing. I want you to do it. See what you get. Send it to me if you're not sure you're right. See it. And maybe in a Q&A session, we can do this if you're not sure. Right? So in practice, they can't make any conclusions off of one test. The probability is actually quite low, even though you think, ooh, a test says I'm sick, I'm going to be sick. No, you're not. You're fine. Actually, it's completely inconclusive. You can't say anything. But a couple of tests saying you're sick, well, then you're in trouble. Now you are, hopefully, as ready as you're going to be to get busy with these questions. I would start with problem 6.4 and then the others because 6.4 is very similar to what we did. Okay. I just want to check here. It doesn't actually matter how many people there are. I copied this from another question. The number of people is irrelevant. The percentage is the only thing that matters. Okay, so don't get confused by that. I want to, in our last 7 minutes, show you something that is interesting. Is the Monty Hall problem. So this comes from a talk show. Let's make a deal where the person selects a door for their prize, and there's a fancy car behind one of these doors and a goat behind two of the other doors. Assuming you're not a goat farmer thinking that's an awesome prize, you want the car. So whenever you pick a door, let's say we pick door one. Can I click it? I click it. Oh, I can't hold down the Alt key, I see. Then the game show host is going to show you another door. I picked door one. I don't know what's behind it. I could be right, I could be wrong. They're going to open another door and reveal a goat because there are always two goats. So one of the other doors will always have a goat. They're going to show you the goat and then ask you, Well, there's a goat over here. Do you want to switch to the door 3, or do you want to stay with your selection? You can then decide, ooh, seems to be 50-50. I'm going to stay. And I get the goat. I should have switched. I'm a loser. So then I can play again. It's not like Lady and the Tiger. These are probabilities. Let's suppose I choose door 1 again. They're random, right? I don't know which door has the car. Oh, he reveals a goat again. There's no logical statements above the doors telling me exactly where the car is. I have to take my chances. So I randomly pick one. They're always going to show me a goat. And then I have the option, do I switch or not? It's like, ooh, last time I didn't switch, so maybe this time I'm going to switch. Oh, and I got the car, but it's random. Sometimes switching will work, sometimes it won't. Let's go with door number 2. Oh, now he shows me a goat. Do I switch or do I not switch? Ah, switching worked last time. Let's switch again. And I got the car again. No, this is completely random, right? I don't know where the car is. Let's pick door number 2 again. And I'll show you the link up here. You can copy it if you want to play. It's maybe a little small, but let me know if you want it. I picked door number 2, right? I'm gonna switch again. Oh, I keep getting it. I'm just very lucky. Of course, I don't know where it is. Eventually, this isn't always gonna work. Pick number 2, get a goat. I'm gonna switch again. Oh, they're not shuffling this very well, but you get the idea. I don't know where it is. Now, let me go back to this. So now, this was presented long ago, ooh, very long ago. Where was this? 1975 in a column called Ask Marilyn, uh, which was done by a person who was, at that stage at least, held the Guinness World Record for the highest IQ. So she answered this question, and then people didn't like the answer. People said she was wrong. Let me just find. Oh, I shouldn't hold my button down and do it. So let's see what she said. There's lots of ways to do this. Let's try and do it. Oh, I'm running out of time here. If you want to stay, I'm just going to keep doing it. So it's on the video. If you need to go, you can watch the video afterwards. Totally fine. I'll speed up a little bit. It's always going to be on the video. I know you would love a goat, assuming you don't want a goat. It's going to mess up my house. So uh, if you have to go, I totally understand. But I'll do it just so that it is in the video. We're going to go a little over time. So what I'm going to do is I'm going to just do it informally. So we speed things up. I have 3 options really. I could have a car selected, door 1, or I could have selected, let's say, goat 1 or the other goat. Let's call him goat 2. Then, so this is 1/3. It's random. I don't know what's behind the doors. I could randomly choose these guys. Then, regardless of which one I'm going to pick, I have the option to switch or not to switch. Little fast now, but you can always rewatch the video. So switch or don't switch. Switch, switch, or don't switch. And switch or don't switch. Those are my options, right? And let's suppose I do it randomly. I switch or I don't switch randomly. Because I don't know what's behind the doors. It's 50-50. Switch or don't switch. Don't know. Now, in the case of So let's say the probability I'm looking for here. The probability I'm looking for is one of them is given I switch, what is the probability that I win the car? So if I selected the car, switching is going to be a loss and this is going to be a win, right? If I've selected the goat, switching is going to be my win. And if I selected goat number 2, switching is going to be winning again. So now let me just make a line here. Now, we don't really have to do a full probability if you just look at this. If So this is going to be a lose, and this is going to be a lose, lose, and this is going to be a lose. We don't actually need the full thing, though you could write it out completely if you want to. If you just look at this, given I switch, these are going to happen, and I win 2 out of the 3 possible times. Now, I invite you to do the whole thing and see, oh, this is a conditional probability. That's backwards again. So I need to write down my 2 conventional probabilities, win and switch, over the probability of the given one. And then you can find the paths and so on, right? Winning and switching is going to be this one. Winning and switching is going to be this one as well. So 2 paths there. Multiply along the path, multiply along the path, and add them together. Over switching in general, if you're not clear on what these squiggles mean, I want you to have some extra practice. But let me know for sure. Just switching, no other requirement. It's the top path. So let's put star, little star. Top path will be, for example, a third times a half. Just switching, whether I win or lose. Middle path here is a switching path. A third times a half for this one. Win or lose, doesn't matter for the bottom one. Bottom path, again, a third times a half. Let's fill this in. Why not? I don't want to be lazy here. There's going fast and then there's leaving out information, right? Win and switch. No, that's a switch and a lose. Win and switch is this one. So it's a third times a half. And they're all very similar, right? Win and switch is also this bottom one. A third times a half. And if you calculate that, it's 2/3, which we could have seen here as well. Out of the switches, 2 win and 1 lose. So 2/3. You can sort of confirm in this case visually as well. So then that's what the person wrote. This person at the time had the highest recorded IQ, and she wrote a little column and she addressed this question. And she said something very similar. You could just Wikipedia search Monty Hall problem, and she said basically the same thing. And then she got a huge number of responses in the mail from PhDs and noted professionals saying that she's wrong. For example, let me just see if you can read this as well. Maybe it's small, I'll read it for you. Scott Smith, he's putting his name on this, a PhD from the University of Florida at that time, said, "You blew it. You blew it big. Since you seem to have difficulty grasping the basic principle at work here, I'll explain. After the host reveals a goat, you now have a 1 in 2 chance of being correct. Whether you change your selection or not, the odds are the same. There is enough mathematical illiteracy in this country, and we don't need the world's highest IQ propagating more. Shame. Because our intuition says, perhaps, mine, sure, that if I select the door, a goat will always be revealed, right? Because there is enough goats that the host always has the option of revealing another goat. Now it might feel intuitively for me That, well, it's 50-50. I have two doors. One of them has a car and one of them has a goat. It's 50-50. Surely. That's exactly this PhD's argument. And many people wrote in at the time criticizing Marilyn's answer. When in fact, if we make the tree run through all the scenarios, run through the probability calculation, whether you sort of visually see it or you actually use the formula and everything in detail, it's not. It's 2/3 because it is unintuitive in many cases to really see how this extra information affects my chances. It's not intuitive for me in many situations. I need a calculation that I can rely on. That's why these things exist, because my feelings don't calculate and incorporate and combine all the factors involved. That this goat being revealed is extra information. It's not 50-50, but I don't necessarily intuitively see what it is. And some people are so convinced about their intuition always being right, they would just criticize someone when in fact they just look like idiots now. And many people did this. When Marilyn in her column was perfectly correct. It is 2/3. And it just demonstrates, and there are other probability examples as well. So they're a little fancy, we don't have all the tools for them, that show how opposite our intuition, our feeling might be. Thinking something is likely, how likely is it? I don't always have a good feeling that's accurate, that I can rely on. I need something more scientific, more objective, outside of my opinion to tell me and to analyze the situation correctly that I can then base sound decisions on. That's why these things exist. So, this is a very well known and hopefully interesting example of how not just me, but many highly educated people can't always detach from their intuition. All right, my apologies for going over and for starting late, and on both of those. Are there any questions about this? If you're watching the video afterwards and you have questions, feel free to email me. Not everyone could stay, I understand, and we won't go over the time too often. Are there any questions or thoughts? All right, we now have everything. Go ahead with the problems. Try and do the virus problems. I think it's problem 6.4. Do that first, maybe, and then after you've sort of gotten used to the tree and how to approach it, then try the others and just be aware of what the question needs from me. There's a lot of words, and the biggest challenge in word problems like this is to just navigate through all those words and to figure out what information is given, and then how will I structure the information to get a plan for finding the probabilities that they want. All right, enjoy the weekend, and I will see you guys later. Thank you.